Okay, so you have already seen a perceptron which takes binary inputs and binary outputs. And then we have seen a XOR example on that. And we have also seen some other gates through this. We have also seen different types of activation functions which we use in MLPs. So today we are going to see MLPs which are used in modern days, which don't take binary inputs but which work with real inputs, and the output can also be real, right? So let us start with one layer perceptron here. So first, we have something called as an input layer, which takes all the inputs or kind of features that we have, right? So here we are denoting them as x1 to xd, where d will be the number of features that we have, right? And this layer is typically called as the input layer. Then in the end, okay, I guess it's not showing up on the screen. Okay, got it. So the last layer is called as the output layer, and it can be a real number, or we can put some kind of thresholding on that, or we can apply some kind of transformation so that it stays in a range, so that we can treat it like a probability, like how we do in a classification task, right? And all the layers which are not input layers or the output layers are known as the hidden layers. So if you see this kind of architecture, we are going to call this as a one layer perceptron, right? So as you might have noticed, the number of layers that we are counting are only the hidden layers, right? Now here you can see that we have two hidden layers, which means this is a two-layered neural network, right? And now we can call it as a multi-layer perceptron, okay? So now we are going to define a convention which we are going to use in almost all of the lectures which involve neural networks. Okay. So in the previous lecture, you have seen terms like Z and A, where Z was the summation term, which is like Wixi, and then if you add the bias, the number that you get, we are calling that as Z, right? And then you apply the activation on top of that, which we call as A, right? So here we are going to introduce a convention. If you focus on the top, we are going to call the first node of first layer as z subscript 1, z superscript square bracket 1, right? So superscript is denoting the layer and the subscript is denoting the node, right? So if you see all the nodes which are present in layer 1, they all have their superscript as bracket 1, which denotes that they are all nodes of the layer 1, and then their subscript is changing as z1, z2, z3, right? So which denotes that that is a node number. This z1 is the first node, z2 second node, z3 is third node, right? Similarly, when we have the activation, we are going to follow the same notation as you can see on the top. When a subscript 2 is node number 2 and a superscript square bracket 2 is the second layer, right? So is this convention clear to you? Is there any doubt? Okay. So the last layer or the layer 3 output is the activation of the last layer. And there also we have a subscript 1, superscript 3, showing that it is a node of third layer and it is just a single node. So it has the subscript 1. Okay. Now, since we don't have any activations applied on the zeroth layer, or which are like our inputs or the data, we are, just for the convention, we are going to extend the same notations here, where we are going to call this input layer as zeroth layer, and thus we are calling it like a subscript 2 superscript square bracket 0, right? Okay, so I hope this is clear. Right. So we are just going to replace x1 to xd as a1 to ad in this fashion. Okay, so now we are going to see how forward pass works for a single node, and then we will slowly expand this to the entire neural network, right? So as you can see, we are just focusing on the first node of the first layer, right? And if you focus on the color codes, we have bias in the green color and then weights from each of the different inputs as different colors, right? So in a way, you can say that the right hand side is just kind of linear regression, right? Where if you have different features, we have weights corresponding to each of the feature and then we add the bias term to that, right? So we can say that an MLP forward pass of a single node without applying any activation is very similar to a linear regression, right? Okay. So here you must have seen a convention that is used for W also, right? So W 1, 1 is used in this orange bracket. So let's see what does that mean. Okay. So the first number is denoting the eighth node in the first layer, and the second number is denoting the bth node of the previous layer, right? Now this might sound a bit counterintuitive, right? That we are taking the taking the next layer indexing as the first and the previous layer indexing as the last, right? But like you can just take this as a convention for mathematical benefits, and like for some libraries choose to do it this way and some other libraries may choose to do it the reverse way, right? But for this course we are going to consider it this way. Okay. Right. So if you see A0, it is going to be of RD or D dimensional. Then we call W1 superscript 1, which is also the D dimensional thing. And Z1 superscript 1 is the summation term of the first node of first layer, which we can write in this fashion. So here it is important to know which terms are scalars, vectors, and matrices, right? So Z is going to be just a scalar, right? And W is a vector of size D, right? Because it is taking weights from each of the inputs, right? And A0 is just the input. So it is also going to have the size D. So the first term over here is just showing the element wise multiplication between the W and A's, and then we are taking the summation over it, right? And then we are adding the bias term, which again, if you notice the notation, we have B subscript 1 superscript square bracket 1, which denotes that this is a bias of node 1 from layer 1, right? So bias is always added to the current layer that we are working on, right? There will not be any biases attached to the input layer, right? Because like input is not a layer to say. Okay. So is this notation clear as of now? Is there any doubt? Sorry, W and A. Okay, so A is just the activation which you get after you apply an activation function on Z. Okay, but currently in this particular slide, we are taking A as the X itself, right? That is just for notation, uh, like A's of notation, we are doing it. Okay, weights, W is the weights, right? A is the input. Is that clear? Okay. All right. So after we compute the summation term, we can apply any activation that you have seen in the previous lecture. So can anyone name some of the activations that you remember? ReLU, sigmoid, 10H, right? These are the different activations which are used for different purposes. But to make it more generalized, we are just calling this activation function as Z. And that is also going to be an element-wise operation, which means that it is not going to make any changes to the shape of Z, right? So in this case, we had Z as scalar. So our A is also going to be a scalar. So that's why we are writing that A subscript 1 superscript square bracket 1 is R of shape R. Okay. Okay, so we have now seen it for a single node. Now we are going to expand this for multiple nodes. Okay. So on the screen now I have shown it for all three nodes of first layer. So if you closely see the differences between these three equations, on the left hand side, you can see that the subscript has changed A1, A2, A3, right? And which denotes the node number as we have discussed. Now, as we go on the right hand side, the weight subscript has changed and it is W1, W2, W3, right? Which again denotes uh, it denotes the node number corresponding to each of these nodes, right? Now input is constant, which means that A0 is not going to change here. And then we have bias corresponding to each of these nodes, right? So is it clear till now? Okay. Right. So now, when we implement neural networks, we are not going to compute each of these terms individually, right? Because that does not give us any computational benefit. So we are going to do something called as vectorization, which lets us compute things in parallel, right? So if you have studied linear algebra, you already know like when we do the vectorization, and then we can use things like matrix multiplication to avoid for loops, right? So here we are going to do a vectorization of these forward pass. So for simplicity, let's assume some of the shapes and like let's assign numbers to some of the shapes. So when I call W as 1 cross 3, where do you think this 3 is coming from? We have just discussed the notation. Let me give you two options. Is that 3 coming because of 3 nodes in the first layer, or is it coming because we have 3 number of features in the zeroth layer? How many of you think it is because of the hidden layer size? Okay. How many of you think it is because the input layer size? Okay, majority here. Right. So as we discussed that the notation in W, like the first number 1 is corresponding to the current layer, which is layer 1, and the second number is for the previous layer, right? So it is considering the number of features that we have in the input layer. So in this example, we have assumed 3 number of features, right? And as you know, each of this equation is for different nodes of the first layers, right? So that's why we have 3 equations, and each of this equation, we have 3 cross 1, where 3 denotes the number of features in the input layer. Does that make sense? Okay. Right. Now, if you try to vectorize this, we get Z as 3 cross 1, and then we can put in each of these W's as rows in this vector, and then becomes 3 cross 3, right? Now, it is 3 cross 3 because we have 3 nodes in the hidden layer 1, and we have 3 features as well, right? So that's why it is 3 cross 3, and then we multiply that with A0, which doesn't change across the nodes, and then we add the bias term of each of the nodes, right? Okay, so once we do this operation, we can rewrite this in a more general format where we call this as Z1, where if you remember, the superscript denotes the layer number, right? So when I call Z superscript 1, what I mean is it is a summation term of layer 1, and then this W has now become a matrix because it is of size uh, like it is 3 cross 3 because like we have three nodes in the hidden layer 1 and 3 in the input layers, and A is a vector and B is also a vector, right? So it is very important to in your mind keep seeing these as scalars, vectors and matrices, right? Then it becomes more easier to compute these things. And like if you don't know, in mathematics, we denote the matrices with capitals, right? So if you read any ML books or any math books, like you will see this notation. So you can just keep that in mind. Okay. And then we can get the activation like this, where we apply the Z as an element-wise operation on Z. Okay. So now coming to the layer 2, we have the same operation, and currently it is written in the vectorized format again, right? What do you think is the dimension of W superscript square bracket 2? 1 cross 2, 2 cross 1. How many of you think it is? Okay, so it is going to be either 3 cross 2 or 2 cross 3, right? So is it 3 cross 2 or 2 cross 3? 2 cross 3, right? Because like the first dimension is denoting the number of nodes in the current layer, right? That's why it is 2 cross 3. So I think now the conventions are clear, and let's see the forward pass of the final layer. So in the final layer, you multiply the W3 with A2 and then add the bias term to it, and we get Z3, right? Which is, if you apply the activation on top of that, we get the Y head. But in neural networks, you generally don't apply activation on the last layer, right? So can you guess any reasons why we should not apply an activation on last layer? Let's consider you are doing a regression problem. Right. So one of the reason can be like, let us say you are doing a regression problem and you use ReLU as an activation. You will never get negative numbers, right? Because ReLU will just zero out all the negative numbers. That is one of the reasons. There could be more reasons. Yeah. Okay. All right. So now we will try to generalize things more, and we will try to directly think about the shapes of A, B, and W here, right? So here there is an, again, we are introducing a notation. A0 is the input layer and it is of RD, but we are going to also denote that as N superscript 0, right? Which means that it is number of nodes in the zeroth layer, right? So if we just continue this convention, we can denote the number of nodes in any layer as N superscript L, right? Which where L will mean that this is of Lth layer. Right? Right. So this way, if we have to see what is the dimension of W superscript 1, we can say that it is R N superscript 1 cross N superscript 0, right? Because we have now introduced the notation of N here. And B will be of size N superscript 1 because bias is on always for the current layer. Okay, so this is the summary of shapes that we have. Let's try to go through them one by one. So N superscript L is the number of nodes in the Lth layer. A superscript 0 is the input layer, as you know, and it is the size of a number of features that you have. Then weight matrix of any layer will be of size R N superscript L cross N superscript L minus 1, right? So as I have said earlier, for conventional purposes, we are taking the current layers weights first and the previous layers layer weights as last, right? Then we have bias as size L. Z will also be of size L because it will be of the number of nodes in the current layer. And activation, after applying the activation, it is of the same size because it shape doesn't change. Okay. So let's try to see this through a Pytorch code also. So I'm just trying to define a single layer with Pytorch. I hope this is visible. me try to increase the brightness. Okay. So we are taking the D0 as 3 and D1 as 2, which is like if I connect this to the notation we used in slides, then this is n superscript 0, right? Which means that we have three features in our data set, and then in the first hidden layer, we have two neurons, right? So this is how you can define a layer in PyTorch, which is nn.linear D0, D1. And when you just try to print it, it nicely shows that it has in features equal to 3 and out features equal to 2. And it also shows that this layer has bias term, right? Now, if I do layer.weight.shape, what do you think is going to be the shape of this layer? Like in the slides, we are using the same convention as PyTorch. 2 cross 3 or 3 cross 2. Right? So the current layer nodes come first, right? So it is going to be 2 cross 3. Right? And then if we check the shape of bias, it is 2 because we have two nodes in the first layer. So if we have to iterate over all the weights corresponding to zeroth node, right? We can do it in this fashion because the first index is corresponding to the layer 1, right? Okay. So I hope this much is clear. Is there any doubt thus far? Okay. So we are going to continue. Right. So you have already seen the XOR example using binary input, binary output MLPs. Now let us try to see this for generalized MLPs, right? And though since we are not talking about learning the weights and only talking about the forward pass, let's assume some weights and biases here in this MLP and then see if it is correct for some particular input of XOR example or not, right? So let's first take 0, 0 as the input, and then you know that for XOR, if you pass 0, 0, the output should also be 0, right? So let's see if this neural network is giving us the desired output or not, right? Okay, now fitting all of these numbers into the conventions that we have defined thus far. So A superscript 0 is 0, 0, which shows that this is just the input. You can also replace that with x1, x2, right? Because we are just passing a single example of 0, 0 there. Then we are defining the bias, where the first node's bias is 0 and second node's bias is -1. That's why we are writing as a vector 0, -1. Okay. Now, when we are talking about the weight matrix, you know that the first row corresponds to the number of nodes in the hidden layer, right? So that's why this is also color coded, as you see, that the first two entries are both coming towards this node, right? And that is because rows are corresponding to the different nodes in the current layer, right? So similarly, you can see that second row colors, all of those arrows are coming towards the second neuron of the first layer, right? So I hope this notation is again clear. Now here is how we compute the Z term as we have defined earlier. We multiply the weight matrix W with A0 and then we add the bias term to that. So after doing the forward pass till first layer without applying activation, we are getting 0, -1, right? So I hope it is clear till this point. Then once we apply an activation, in this case we are using ReLU, this -1 is going to be 0, right? So at the end of the forward pass of first layer, we are getting the output as 0, 0, right? Okay. Now we are going to take this forward to the next layer, right? And as you can see, next layer weights are 1 minus 2 and the bias term is 0. So just using the same convention, if we get the summation term z, it becomes 0, right? And in this example, though the ReLU has been applied on the final output, you should remember that generally in when you apply it in real life, activation is not applied on the last layer. Okay, but here it is not making any difference anyway. So we can see that we have verified, we got the output that we wanted. We knew that if you pass 0 0 in XOR example, you are getting 0, and after a forward pass, yeah, sorry. So this A1 is the output of the last layer. So if I just go back to the last slide, this is from where you are getting the A1. It came after we applied the activation on the summation term after doing the forward pass on the first layer. Okay. Okay. So I hope it is clear for this example. Now let's do this activity. You try to work this through for this particular example. Okay. So I'll give you 3 to 4 minutes. Let's try to work this for input 0, 1, and then you can verify if you are getting 1 as the output here. Meanwhile, if you have any questions, you can ask. Okay. So in interest of time, I'm going to move forward. So I hope many of you are able to solve this. Okay. So all we do is replace the input in the previous computations, right? So after doing the forward pass through the first layer, you should have got the output 1, 0. And then after doing the forward pass through the second layer, we get the output as 1. Okay, so thus far in our discussions, we already only took a single example, right? But that's not how we do machine learning. In real life, we have been given like a data set which consists of n examples, right? And we want to learn a model which generalizes over these n examples and beyond, right? So that's why we want to learn weights and biases which kind of generalize over the number of examples, right? So now we are going to see the computation, like we will just expand the computation for n examples, right? So here we are again introducing a new notation, as you can see. So x subscript parenthesis I will denote that this is ith example, right? And when we are talking about a single example that we did thus far, we will see that its shape is D, or in another notation, n superscript square bracket 0, right? So I hope this is clear. Now we can denote each of the examples as a different rows in this matrix, right? So that's why it is x subscript 1 to n, right? And then with the same notation that we used earlier, we just replace that with a superscript 0. So finally, our A is going to be a matrix of size n cross n superscript 0, right? Where the first n is showing the number of examples and second n superscript 0 is showing me number of features. Okay. This is also how you pass the inputs in your linear regression or any scikit-learn model that you use. Right? Right. So now if we see, if we try to work out the forward pass, like if you notice the W and B are independent of I, right? And this is what we just discussed, that your weights and biases are independent of your number of examples, right? They should generalize over number of examples. The A term is dependent on number of examples, right? That's where we have A subscript I, where I denotes the ith example. So if we do this computation, we are going to get a summation term z, which is of size n superscript 1, right? Which where n superscript square bracket 1 shows the number of nodes in the first layer. Right? Same thing, we are just trying to vectorize this over n examples. Okay, so here we are showing it for 1 to n examples, right? And then each of these z is of size n superscript square bracket 1. Right? So if we try to put this through different rows of a matrix, we are going to get n cross n superscript 1. Right? And till this point, we have done the forward pass without applying activation, right, on n examples. So now you can connect these shapes that we started with A0, which had shape n cross n superscript 0, and finally we got Z, which is of n cross n superscript 1, right? So as you might have noticed, as we keep doing the forward pass, this n will not change. The only n superscript 0 will become superscript 1, 2, 3, 4, and so on, right? Based on the number of layers that you use in your network. And even after applying the activation, the shape is not going to change because activation is an element-wise operation. Right? Okay, so let's try to see a shape of different components in that example, right? So A0, as we discussed, it is n cross n superscript 0. W1, it is n superscript 1 cross n superscript 0. Bias is n superscript 1. And then there is something interesting here, which is about the bias term, right? So you know that bias is also not changing for different examples. But if you try to add the multiplication of W and A directly to the bias, it will not work, right? Because in mathematics, if you have to add matrices or vectors, they should have same shape, right? But in computers, in libraries like NumPy or Torch, there is something known as broadcasting, which allows you to multiply or sum the vectors or matrices which are not of the same shape, right? With some rules, right? So in this case, what will happen is that even if your bias will have 1 cross n superscript 1 shape, which is going to be for a single example, if you try to add that to n cross n superscript 1, it will automatically vectorize over the first dimension, right? But for the mathematical, here for the mathematical explanation, we are just saying that we are manually doing the vectorization here, right? Where each of the entry in this matrix is the same. Right? This is known as the broadcasting, where we just copy some of the elements over a particular dimensions, right? Okay, and finally we can write our z like the following. And in this final equation, you can verify that all shapes will match because you have manually vectorized or like broadcasted the B matrix. Okay. Right. So in a nutshell, you can you can say that a forward pass of a single layer of neural network can be summarized in these two equations, right? Where you get the summation term by doing the linear regression kind operation, and then you apply an activation on top of that. Okay. So is it clear thus far? Any doubts? Yeah. Right. So let's try to work this out. So the question is that should, in the last equation, should the W transpose come first or A0 come first, right? So A0 has the shape n cross n superscript 0, right? And W1 is having shape n superscript 1 and superscript 0, right? So if you transpose that, it will become like this n superscript 0 shape will come first, right? And then only the matrix multiplication will become possible, right? Because in matrix multiplication you should have the same shape in between, right? So when you multiply these two things together, you are going to get n cross n superscript square bracket 1 shape, right? So is that clear? Yeah, it should work for all the cases because we are not assuming any particular thing here, right? Because all of these things are variables, right? So am I understanding your question correctly? Okay. Okay, so now let's try to work out our XOR example end to end with all the examples we have, right? So in XOR, we have four different inputs possible, and then here we are showing four corresponding outputs or the ground truth for each of these examples, right? We are going to use the same weights that we have shown in the diagram previously, right? Uh, as discussed previously, we are doing this broadcasting of bias term here. So when we try to work out the math, here we are going to have a 4 cross 2 matrix, which is A, and then we multiply that with 2 cross 2 weight matrix, and we add that to a 4 cross 2 bias. Right? After that, we are getting a 4 cross 2 output. Right. So after we got our Z superscript 1 output, we apply the ReLU activation on that. And you can see that this -1 entry has become 0 because we have applied ReLU here. Right? Now, using the weight matrix from second layer, W superscript 2, we again vectorize or like broadcast bias, which is 0 in number of examples shape. So it becomes 4 cross 1. Right? And when we do the complete computation, we get the final output as 0110, right? So at this point, we can consider that the entire forward pass has been completed. But like, yeah, if you try to generalize things for all layers, if you try to keep it same, then we have also applied ReLU here. But as I'm repeatedly saying, we don't apply ReLU or any activation on the last layer of a neural network. Okay. So yeah, till this point, we have done a forward pass on the entire data set, which is a representative enough, right? So in real world, if you have any n cross d data set, you can work out and write your own MLP, right? And then do the entire forward pass like this. Okay, so this lecture was a bit involved, right? So there are many conventions that we introduced on the way. So I would suggest that you go through the recording again, right? And then try to work it out yourself to understand it better and better. So now let's talk about the number of parameters, right? Because you must have heard sometimes that some neural networks have so many parameters, and then some of them don't have that many parameters, but they work very well, right? So it's kind of important to know how many number of parameters you have, because that will impact on the memory and the computation time. So how do we compute the number of parameters of an MLP? Right? So let's try to see different shapes that we had. This n superscript 0, which is the number of features that we have, it is 2, right? In the XOR example. In the first layer, we had 2 neurons, and in the second layer, we had 1 neuron, right? So these are the shapes of neurons. And then if we check the shape of W superscript 1, it is going to be 2 cross 2, and it amounts for 4 parameters. Then the bias in the first layer, it also going to be of size 2. Then we go to the next layer and we get the W as 2 cross 1 size, which has 2 parameters, and then it has a scalar bias. So it is going to be 1. So finally, we can say that in this example, we have total 9 parameters, right? Because 2 cross 2, 4 for the weights, for 2 weights for the second layer, so 6, and then 3 bias terms. So it becomes 6 plus 3, 9 parameters. So in general, as we discussed, we can use this kind of formula to calculate the number of layers in our neural network. Okay. And this is just for a vanilla neural networks. Okay. If you go towards more complicated neural networks, things may change. Okay? But this neural network is like sufficient for many of the applications that you work. Okay, so I think this was all we had for the slides. Now we will go through a notebook, but before we move there, like if there are any questions, we can take them. This is for one example. No, because the number of parameters will not depend on the number of examples, right? Because your neural network or your linear regression or any model, right? They are like independent of number of examples that you use. Weights are independent of them. Okay. You mean in the parameters or the slides before that? Should I go in backwards? Okay, you mean the forward pass using all the examples, right? This part. Okay. So let's try to work this out a bit more slowly. We have the input X as 4 cross 2, right? So each row in this matrix is denoting different inputs of the XOR examples, right? It is 0, 0, 0, 1, 1, 0, and 1, 1. And then on the Y, we have corresponding outputs, which is 0, 1, 1, 0, right? Now, this weight matrix is of size 2 cross 2. Why? Because the first 2 is coming because of the number of nodes in the current layer, which is 2, and the second 2 is coming because of number of features, right? So number of features in XOR example we have is 2. And these are some weights that we know are working for the XOR example, right? So we have not discussed the learning of weights yet. And then bias is going to be of the same size as the number of nodes in the current layer, which is again 2, right? So if you try to then broadcast it, it becomes like that in 4 cross 2. And then when we try to get the summation term, we just multiply A with W and then add the bias term there. So yeah, is there any doubt here? Okay. Yeah, it may take some time because like we are just trying to go through this in limited time that we have, right? Any other doubts? Okay, so like I would say that it is quite hard, right, to think it through different shapes, then converting these scalars to vectors and vectors to matrices and all, right? What if we had a tool by which you just need to know a bare minimum example, which is like a linear regression, right? That you just multiply W's with Xi's and add the bias term. That's very easy to understand, right? Nothing complex there, no matrices, no vectors. So if you could just work it out, that bare minimum example, right, without worrying about all these reshapings and stuff, like that would have been much more easier, right? It would not cause the mental strain that we are getting through while thinking about the vectorization, right? So there is a recent tool called vmap, which is introduced in Torch and JAX both, right? So that we are going to see through a notebook. Using this, you can just intuitively think about the vectorization that you want to do on different dimensions, and then you don't have to go through all of this. Okay. So let's try to see how to do that. So this is just a two-layer neural network defined by Torch. Okay. So we have already discussed this, so I'll not go through this. These are just the shapes that we just discussed in the slides, right? Let's dive into the vectorization with torch.vmap. So we are going to use three different libraries here, or I would say three different functionalities. One is torch.vmap, which we will finally use to do the vectorization. One is the JAX typing, where the name suggests JAX typing, but it also works for Pytorch and NumPy and some other libraries as well. Okay. And then the third is the beer type. We will go through what is the use of each of this. Okay. So let's try to quickly understand what is JAX typing and why I'm introducing that in this lecture. Okay. So sometimes when you write the code, it is hard to get what is the shape of each of these terms, right? When you read a math book, it is clear that whatever is a matrix is denoted as a capital letter, right? Whatever is a vector, it is denoted as a bold small letter, and whatever is a scalar, it uh, is a like a lowercase number without any bold, right? So what if you had a way to do this the same thing in code, right? So then we will make less errors while writing the code, right? And it is also more readable, right? If you try to explain your code to anyone else. So let's start with the scalars. So how do you define a scalar in using JAX typing is like this. We have imported this float directly from JAX typing, which says that my input type is a float, right? Then as the first argument, we are passing the kind of tensor that we are going to pass here. Since we are working with PyTorch, we are passing tensor. If we are working with NumPy, I would pass np.ndarray here, right? Which just shows the typing. And the second argument here is defining the shape. Okay. So when I execute this, I have got the scalar type, and then I have tried to define a scalar using torch. Now I would try to mention here that shapes that we discussed in slides and then shapes that we see in PyTorch and NumPy, there is a slight little bit of difference there. Okay. So what is the difference? We will just see. If you see the size, it shows empty here, right? Which shows that it has no size. But ideally, how you would write this in math? You would have written it as size 1, right? Or maybe 1 cross 1 or something like that. But in libraries, each of these things have different meanings, and that's why they are not the same thing. Right? So here I would call this a scalar, and let's try to check if the scalar is of instance scalar type. So if you have not used this command isInstance before, it takes the first argument as any object, and the second argument is the class or the type. And if this object is of this type, it will return true to us. Okay. So here in this case, it is showing true, which means that the scalar is of scalar type. Now I try to define it in this slightly different way. You can see that it is the same number, but now it has shape 1. And now I would argue that this is no longer a scalar, but it has become a kind of vector, right? So that's why we don't go into terminologies of vectors, scalars, matrices when we work with libraries like NumPy, right? We call them tensors, and then we talk about like how many dimensions it has, right? For example, here I would say that this has 0 dimensions, this has 1 dimension, right? So you can just like put this into an umbrella of tensors, and then we can say this is a zero-sized, zero-dimensional tensor. This is one-dimensional tensor, right? And if I try to check, this is returning me false, right? Which clearly shows that this is not a scalar, right? Now let's try to define a vector. So here only change I made is that I put n here, which denotes that it is a vector. And if I try to put this non-scalar, which was a vector in isInstance, I'm getting true, right? Now let's define another vector of size 2 and try to check the isInstance. It is again returning me true, which means that as long as I pass any vector which has 1 dimension, it is going to return me true here. Okay. Now let's talk about matrices or two-dimensional tensors. So if I try to pass a vector in it is going to be return me a false, right? But now I have defined the matrix because this has 2 dimensions. And when I try to check, it is returning me true. Okay, I can define a more complex matrix like 2 cross 3 shaped, and it will still return me true here. So this is all about scalars, vectors, and matrices. But sometimes in machine learning, you can go beyond 2 dimensions as well, right? Let us say you are working with images. Then 2 dimensions are just for your width and height. Then you may have a batch dimension. You may have number of channels, right? So then it can go up to 4-dimensional tensor. So in those cases, you can define your tensor type like this. And now I have defined a 2 cross 2 cross 2 tensor, and it is going to return me true because this matches with B0, B1, B2, right? And here you have the flexibility to give any name that you want. So in class, we discussed that we were denoting the number of nodes as n superscript 0 and superscript 1 like that, right? So instead of B0, B1, B2, you can also write N0, N1, N2, right? As you want. So this was all about the JAX typing. You can, how do we use this? We will go through that. Okay. Before that, let's go through a quick intro to beer type. Okay. So what beer type does is that once you define this kind of types for your functions and your classes, it will ensure that if you pass in any other shaped tensor, it will return you an error, right? It will not let the forward pass to happen. So some of you might have noticed that when you work through the linear regression example, when writing the code in Torch or NumPy, if your y is not n cross 1, but it is just n cross, or it is just n sized, right? You get into troubles because libraries will do the broadcasting and stuff, right? So to avoid that, we can use beer type. So let's see a simple function which says call my name, and if I pass a name to that, it will say hello and then the name, right? So if I say call my name John, it says hello John, right? But if I just pass some number to it, it doesn't know that I have passed a number, right? Now this is a bit similar to how languages like C is working, right? Where you particularly define the type of input that you want. In Python, like it can be of any type, right? And because of that, we are having these issues. But we are trying to solve it in a different way. Now, those of who you don't know how to define the types in Python, so you can see it here. In this function, the argument is name, and then I have defined colon str, which means that it is of string type, and then this arrow str, which shows that whatever comes out of this function or returned from this function should also be string, right? So when this typing, this is generally known as typing, when these type annotations were introduced, they were mostly for readability, right? That you know when you read the code, what is the input type and the output type, right? But we can also enforce these types on the functions. So I'm now calling it as secured call my name function. I have just decorated with beer type, okay? And now if I pass John to this, it is working just fine. But if I try to pass a number, it is raising an error, right? So same concept can be used for the shape definition that we have just seen before. And we can put a particular shape here. And if the shape of array that we passed here is not matching that type, it will return an error, right? So this is, I would say, a faster way of maybe writing your assignment or your project codes, right? Where you will not go into the blind errors where you expected an n cross 1 array, but then you just passed an n sized array, right? So we can also see the error message here, which shows that parameter name 123 violates type hint string as int 123 is not instance of string. This is very clear, right? Okay, so now is there any doubt in these two libraries? Any questions? We are just checking very simple functionalities from both of this. Okay, things will become more clear when we go into the real vectorization. Okay, so as we discussed in the slides, there are two places where we do the vectorization. The first place is next layer's neuron size. Let me go back to the slides. Right. So here we discussed a forward pass over a single neuron, right? And then we tried to vectorize over the number of nodes in that layer, right? So this is one place where we can do the vectorization. And the second place is the number of examples. Because you know that for each example, my forward pass procedure is not going to change. So I can simply do the vectorization there. So these are two places where we can do the vectorization. Okay. So for a moment, let's assume that we have 50 examples. And I think recently sir mentioned in the channel that like when you write assignments or something, you should first try to pass some dummy inputs into that, right? To see if your functions are working correctly. Instead of writing the entire code at once and then trying to debug it, right? Which generally takes more time, right? So first we will try to see this function with some random inputs, and then we will do the real vectorization. So my A here is just the input of n cross D0, which is where my D0 is 3. So this turns out to be 50 cross 3. Now this is the function where the entire computation is done. Okay. Everything that we will see after this is going to be intuitive. Okay. So let's try to see what are we doing with this forward pass. This is done for a single neuron of a single layer, right? And you can see that we have very clearly defined shapes of each of the inputs. First input is A, which is like for the zeroth or the first layer, it is going to be X itself. And for the subsequent layers, it is going to be output from the coming from the previous layer, right? And we are saying that it is of shape D0, right? Which means that it is the shape which is coming from the previous layer, right? Because we are going to vectorize over these dimensions. So we are only talking about this dimension. Okay. So that's why I'm calling it as D0, and let's call this as D1. If you go one layer forward, you can then call this as D0 and this as D1. Okay. So now you know what D0 means here. Then we have a weight, which is also a vector and which is going to be of D0 shape. And then we have a bias, which is a scalar. You must have noticed that this first line is just linear regression, right? We are trying to multiply the weights with their corresponding features. We are doing the summation and then adding the bias term to that. And then the only change we have in neural networks is that we are applying an activation on top of that. Okay. So here we are using the ReLU activation from Torch functional, which you have imported over here. So you can use this functional to leverage various functions implemented in Pytorch. Okay, so this is all you need to define without going into the details of mentally understanding the vectorization of shapes, right? So let's see what happens if I try to pass exactly same dimensions as we have defined before, right? I'm just defining a dummy A, dummy W, and dummy B, where A and W are of size D0 and dummy B is a scalar. So in Torch, if you have to define a scalar, you cannot do something like rand1 because it will give me a it will give me a tensor of shape 1. But if I just do and pass an empty tuple, it will give me an empty shape. Okay, and this is what we have defined over here. So let's try to see if beer type is able to save us from the error. Okay, let us say by mistake I have just defined this as size 1 and then I am trying to do a forward pass. Okay, it is not letting me do the forward pass because I have violated the definition that I have given here, right? And this can save you hours and hours of debugging. Okay, if you try to implement this. Now let's make this as correct shape, which is a scalar, and then do the forward pass. We get a scalar, right? And let's connect this with here. Here we were discussing that this z is a scalar, right? And that's exactly why we are getting a scalar from this function. Okay. Now, earlier we have defined a neural network called model. So if I just pass the A0, which is the zeroth example, and then model.weight 0. Now this 0 is going to be the index of my first node of the first layer, right? And it will have, it is a vector, so it will have all the weights from my previous layer, right? And that's what we have defined here as D0. D0 is size of neurons from the previous layers. So this forward pass is working. Now let's see how can we do the vectorization over the next layer's neuron size, or in this context, let's call this as D1. Okay. So we can just see that This function takes three inputs, A, W, and B. We just try to think that if I try to do the vectorization, what shapes are changing and what shapes are staying constant, right? That's all we need to know to use a torch.vmap to do the vectorization. Okay. Now A is the output coming from the previous layer, or it is the data set. So that is not going to change, right? It is D0 equal to 3, and even if I do the vectorization, it is going to be D0 equal to 3. Now my weight matrix, which is D0 equal to 3, it is now becoming a D1 comma D0 because I am trying to vectorize over D1, right? My bias will also become D1 from a scalar because I am trying to do vectorization over D1, right? This is similar to what we discussed here, right? We are trying to do the vectorization over all the nodes. Now, once we know this much, this is how you can write a vmap function. Okay, so let's try to go through this. Torch.vmap. I'm just passing the forward function that we defined over here. Then in dimensions, I'm just denoting that you have to do vectorization over which axis of your input. Okay, so first I'm passing none, which corresponds to A, which means that I don't want to do any vectorization for A, right? That's why I have passed none here. For the second argument, I have passed 0, which corresponds to W, which says that I want to vectorize over the first dimension of W, right? And I know that my W will be of shape D1 comma D0. I want to do vectorization over D1, that's why I'm passing 0. If I wanted to do vectorization over D0, I would pass 1 here, right? So I hope that is clear. And then we pass the bias term, and there also we want to do the vectorization over the 0th dimension. And here for the like I've just given out dimension equal to 0, but it is implicit that your output will also get the D1 sized here, right? So let's define this torch.vmap will give me a new function which then I can use then as a vectorized function. Okay, so I'm calling it as v1 forward. Let's define that, and then I can give a single example to this function because I have not yet vectorized over the number of examples, right? So A0 is going to pass the 0th example from A, and then I can pass my entire weight matrix and bias into this. Okay, so let's see what were the shapes of weight and bias. So weight dot shape is 2 cross 3, and bias dot shape is 2, right? So we are doing the vectorization over these two, right? Because bias is also of 2 size and weight is also of 2 size. Once we do this, we are getting output of size 2, which is what we thought, right? D1 should be the output size, and it is D1 equal to 2. Okay, so is there any doubt till this point? The key point is how to define the vmap function here. Okay, so once we do another set of vectorization, which is vectorization over number of examples, it will become more clearer. Now let's try to think through it again. Now here we will take the vectorized shapes that we had here, because we have applied the one round of vectorization over using vmap. Now let's say I'm just copying this and putting it here, and now trying to do the further vectorization. Okay, so now my A had D0 equal to 3, which is number of features, will now become n comma D0, because now I'm including the number of examples as well, right? So this three-dimensional tensor is now becoming 50 comma 3 dimension. Okay, my W doesn't change, B doesn't change, because as we discussed, W and B don't depend on the number of examples, right? But my output will now have shape 50 comma 2 instead of just 2, right? Because output will include the number of examples. Now this is how you define this particular vmap operation. We passed the v1 forward function, which was the vectorized function we defined earlier. Then we are passing 0, which corresponds to n for A, and then for the W and B we are passing none none. because we don't want to do vectorization over there, right? And then again, we are passing out dimension as 0 here, which means that whatever vectorization has happened, it should come as 0th dimension in my output. Okay, so what do I mean by this? I'll just try to show. When we run this, we get a 50, 2 output. Okay, but if I wanted this 50 to come as my second dimension, I would just pass out dimensions equal to 1, and then my shape changes from 2 comma 50, right? Why this happened is because it knew that a, a function which is not vectorized should return me a two-sized output, but then I want to put this 50 as my first dimension. That's why it came in the first dimension, but typically we want it at 0th place. That's why we pass it as 0. Okay, so this is the complete procedure of vectorization using torch.vmap, and we didn't have to think through the different shapes and matrices and doing the transposes and all those stuff, right? All we needed to think was like, what is my shape before, and after vectorization, which tensors or which components are going to be vectorized over which dimensions, right? That's all we need to think about. Now let's compare that with the torch model's forward pass. So I'm just passing the same A to my model and applying f.relu because we have already applied the activation in our forward function, right? So if we compare these two, we are getting is true, which means that if I just did a forward pass through a torch model versus I did a forward pass through this worked out torch.vmap vectorization, I'm getting the exactly the same output. Okay, and then in the end, let's just try to see the XOR example. I think this is not that important, but the part covered till now was very important. So let's try to spend some time if you have any questions. So I'll try to put this notebook up so you can like go through it again slowly also. Okay. But these are some like good practices which will save you some few hours of debugging that you have to do, and it also makes your code more readable, right? So yeah, I think we are out of time as of now. So yeah, thank you.